Okay, so welcome back, everybody, for the new episode of the Crosse Thinkers Podcast. And today we have Dr. Shauna Sallmen from the Department of Physics. And thanks for joining us today. And we will be talking about astrophysics. And this is actually a recommendation by one of our neutral students, Hannah. So I will start actually with a question what Hannah wants to ask you. What inspired you to get into physics, especially astrophysics?
Well, I am not one of those people that has I was looking up at the stars when I was 8 story. Or
I was hoping that.
I am not one of those people. I was always curious about everything in the natural world. I'd read about biology. I'd read about, chemistry. I'd read about astronomy. It was always one of the options. And then I guess in high school, I liked physics and I liked math, and they didn't do astronomy. And I went to university and I thought, well, I'm going to do something with physics. Might be math with it, might be astronomy with it, I'm not sure. And in the end, it came down to I was looking at the required courses for the programs and decided one upper division course sounded better in one program than the other.
What was that class?
It was an upper division experimental physics lab or an upper division research project in astronomy.
Wow,
so it was
it's hard
the
to tell
research.
which one's better.
But I mean, it was like, oh, that, or oh, that. So I wasn't real, I don't have I kind of just followed my nose and made decisions, and they panned out in the way I'm here.
Great. So you're studying exoplanets, according to what I get, and for now, but how did you actually started? I read in the slides you sent me, you started with gravitational waves and then migrating through multiple topics.
Yeah,
how did you end up with this?
I have really been all over the place in topics throughout my career. I started as an undergraduate thinking I was going to be a theoretical cosmologist, and I was working on some computer simulations of particles in galaxies to explain that might simulate and model what we see. And then I went to grad school, and I thought that's what I was going to do. And I sort of started using a project to use pulsars to detect gravitational waves, which are these cool things. And then I, in the end, got interested in the pulsars themselves. So I studied pulsars, which are, a pulsar is this really cool thing. It's a neutron star. You take something, the amount of stuff that's in the sun, and you pack it into something that's about 15 miles across. And then to make a pulsar, it's got a really strong magnetic field, and you spin it, the ones I was studying, hundreds of times a second, up to 700 something times a second. And it sends out a beam like a lighthouse, and you detect it every time the beam sweeps past you, it pulses. So I just thought those were really cool objects. I wanted to know how they work, and I still do, and we don't know.
Interesting. So let's start from there. So you mentioned you're doing something on interstellar medium. Is that related to a pulsar star? Or?
No. So I got into
that's another new one. Okay.
It's another field entirely. Well, I looked at the interstellar medium a little bit. It turns out the pulsar signals have to travel through it. It's the stuff between the stars, interstellar medium, so stuff between the stars. And the pulsar signals have to go through it, so they get affected by it. So one of the projects I kind of worked on was looking at how the material left over from a supernova explosion of a star affected the pulses, so you could study a little bit about the supernova remnant. But I wasn't interested in the interstellar medium. I thought it was dull. I avoided the course. I was sure there was one thing I wasn't going to do. It was the interstellar medium. So note to listeners, you can't plan where your life's going. But then when I graduated, I had been sick at the time. It was the time to apply for jobs, so I hadn't applied to many jobs. I had no job. I'm sitting around going, now I have a PhD in astronomy. What am I going to do with it? And after a while, someone I knew from church who was also an astronomer called me up and said, you still looking for a job? I'm like, yep. He's like, we need someone to analyze data. I'm like, okay. And I started looking at the project. I'm like, it's the interstellar medium. Oh, dear. Next thing you know, that's what I'm doing.
So for those kind of mediums, how do you analyze it?
There's a lot of different ways. The way I focus on right now when I'm doing my interstellar medium projects is to look at the neutral hydrogen. And the neutral hydrogen is everywhere. like 75% of the universe is hydrogen. So there's hydrogen everywhere. So there's a lot of it. And neutral hydrogen spits out radio waves with a particular wavelength of 21 centimeters. And radio waves, they're not sound, they're just another kind of light that we can't see. And so it spits out this very particular wavelength of radio waves, and that's the wavelength I look at it and study the interstellar medium with.
So basically, they send those kind of radiations all the way around, and we capture them on the Earth.
Yeah, we capture them, and so you figure, you look at different direction, you see how much there is. You look at different direction, you see how much there is, and then we use the trick of the Doppler effect. And you've probably heard the Doppler effect. When something goes past you, you hear if a car goes past you. So that high pitch and that low pitch. The high pitch is a higher frequency sound. The object's coming towards you, so its sound waves get bunched up. Mm-hmm. And the sound waves being bunched up, you hear as a higher pitch than is being put out. And when it goes away from you, the sound waves it's putting out are getting spread out because it's moving away from you while it's spitting out its waves. And so you hear a lower pitch sound. Light does the same thing. An object moving towards you that's spitting out radio waves, you will observe those radio waves at a shorter wavelength. And if it's going away from you, you'll observe them at a longer wavelength. So by looking at how far to long or short of 21 centimeters you get it, you can figure out how fast the stuff is moving. And because of the motions in our galaxy, that lets you figure out, sort of mostly distinguish things at different distances.
Okay, so you know how far they are from us.
Sometimes yes, sometimes you just know they're at a different distance than the stuff at another speed, because it's more. It's not as simple as. I wish it was simple. Distances is really hard in astronomy.
Yeah, okay, so does this thing have to move with respect to Earth in this direction, or actually, if the thing is moving in this direction?
So it's got to be towards and away.
Towards.
That's all you
get. Does it have to be perfectly towards, or actually?
No, as long as there's a component towards or away, you're getting the component towards or away.
So you can roughly tell.
Yeah.
Great. So, could you also talk about what you had in your slides, which is HI shell?
So HI is astronomy code for neutral hydrogen.
Oh, okay. So it's neutral hydrogen
it's
shell.
H1. It's Roman numeral 1.
Okay.
So yeah, it's H1 is a neutral hydrogen shell. And so I was talking earlier about exploding stars. So stars during their life, they give off all kinds of so during a star's life, there's usually a period where there's a strong wind. Our sun is putting out a solar wind, mm-hmm. but later in a star's life, or different kinds of stars have stronger winds than ours do, and those can sort of blow a bubble in the material around them, and they're sort of pushing the material away and building up a ridge of neutral material around them, like a snowplow. If you think about a snowplow, it builds up a wall of snow. We're building up a wall of hydrogen gas. And it can also happen when a star explodes. That hot material pushes out and blows a bubble. So they're basically bubbles in the stuff between the stars, except what you're seeing is the edge of the bubble where all the material's been pushed to the edges.
I see. So that's a H1 shell.
That's a neutral hydrogen shell.
Is it always spherical, probably?
They'd be spherical if there weren't multiple ones interacting and the interstellar medium was uniform, but it's not.
Multiple ones interacting, you mean multiple shells coming from the same star or different stars?
Different stars. So stars
So
often,
this thing's big, probably.
Yeah,
okay.
they're big. Putting it in, so light year is the distance light travels in a year, and these things can be hundreds or even thousands of light years across because after they've grown for a while. So the interstellar medium, I said it's the stuff between the stars. It's really uneven. It can have densities of like 0.1 or 0.01 atoms per sugar cube size volume, or 1,000 atoms per sugar cube size volume, or maybe 1,000,000, which is way less than here on Earth in our atmosphere.
Can you give us a number? Like, what's the density on Earth, or like outer space of Earth?
I can't remember the number in air, but it's something like 10 to the 20 per.
Oh, that's way more.
I mean, yeah. I mean, it's like I don't remember the number because it's so much ridiculously bigger that it's not.
So it's basically empty.
It's basically empty, and on average, it's about 1 atom per cubic centimeter. And the only reason we can observe it is there's so much space in space that there's a lot of stuff. Mm-hmm. So it's almost empty, but not quite. And so
And it just-
so that's why when you put energy in, it blows a big bubble because there's not that much stuff to push aside.
Interesting. Is this somehow related to dark energy or dark matter?
No. Do you want the
Oh.
long answer?
Yeah, because when I was trying to read something online about dark energies, people are asking like dark matters and dark energy. People are saying why the density is so low.
Yeah, so I'm just talking about the density of the material between the stars in our galaxies.
Mm-hmm.
Then there are many, many galaxies widely separated.
Mm-hmm.
And what they're talking about is the overall density in the entire universe,
Oh.
including all the space between galaxies. And dark matter is something about the way the gravity the way we look at how things move. We use our understanding of gravity to say how much stuff there is. And then we compare that to how much we see. And there's a bunch of stuff that seems to have a gravitational effect that we can't see at all in radio waves, ultraviolet, infrared, X-rays, gamma rays, visible light, nothing. It's just not visible in any way.
That's the word dark.
That's
come
the
from.
dark matter.
They
That's
don't-
what, yeah. We basically said, so there's invisible matter, and called it dark matter. And I mean, after enough years and enough people making testing it multiple ways, most people think it's there. There's a few people saying, well, obviously we just got to change our understanding of gravity.
Which involving
Which
changing the
could
formula.
be, the problem is every time we test our model of gravity, it works. So you got very few clues. And dark energy is kind of the same, only it has to do with how the universe is expanding on very long, like when you look back into the past, the history of the universe doesn't seem to match what we'd expect. And so we invoked a mysterious repulsive force that opposes gravity and called it dark energy.
Is it fair to call it anti-gravity?
More or less, but I mean, we don't really know what it is, right? They gave it a name. It sounds like we know what it is. But the equations basically, you can make the equations match the observations if you've got this term here and and it behaves really unlike anything else we know of.
Interesting. So, since you mentioned the equations, would you mind to elaborate a little bit, because I receive this question a lot. That is, what is first principle
For the
for cosmology?
For cosmology, well, the first principle is general relativity, which is not an equation I can pop off my head. It's like a 4x4 tensor equation, so 16 element tensors. So it's not pretty. You can get essentially the same equations for how the universe should evolve with time by cheating and using Newton's law of gravity instead of Einstein's more appropriate law. And just basically you use things like thermodynamics, how heat flow affects energy of things, and put that with how pressure and density are related, and put that with how gravity would be slowing down, would be affecting stuff. And you do some stuff that is somewhat questionable mathematically, but turns out to give you the same answer as the GR thing. So you do it because you can. And it's basically, you just say, if I have this much stuff and it's expanding outward, but gravity's trying to hold it together, what will happen?
Mm-hmm.
And it should be slowing down because gravity's trying to hold it together. It should be expanding less rapidly.
So
And it seems to be speeding up. So there's something else.
So starting from the equation, you kind of have an expectation, and then you go and take the observation, and now they don't match. You came up with something, and that's probably where dark matter and dark energy come from.
So that's definitely where the dark energy comes from. The dark matter is more like observations within a galaxy or between galaxies.
Which I think is which we can actually take the
Yeah,
observation. Right?
you can also get estimates of dark matter from cosmology by comparing like the baby picture of the universe from very early in the universe to what we see now. And the only way to match that baby picture is to have dark matter and dark energy.
How do we get the baby picture?
It's a good thing I'm teaching cosmology right now because this is all fresh in my mind.
Awesome.
The early in the universe, it was really hot. It was really dense because if you take the amount of stuff in this room and you pack it, 10 to the 30 times less volume, it's going to be dense. It's going to be hot. It's going to be packed together, except that the universe just keeps going on forever. So all I can look at is a piece of it at any one time. I'm looking at this little piece. It's really hot. It's really dense. And It's so hot and dense that the light can't, the electrons are all stripped out of the atoms. You've got a plasma. And the light that's being produced by the hot material can't go anywhere without running into electrons and getting redirected. So that's the universe is what we call opaque. Light can't travel freely.
It's blocked, basically.
Yeah, and as the universe expands, it cools off. As it cools off, eventually the electrons can recombine combine for the first time with their nuclei, so you get neutral atoms, and the light no longer has enough energy to knock them back out of the atoms, so now you don't have electrons floating around, and now the light can travel freely. So now that light has traveled freely. That happened at about 3,000 Kelvin of temperature. Kelvin is Celsius plus 273.15. I don't know what it is in Fahrenheit. I'm sorry.
Yeah, I got used to metrics eventually, right? Yeah, if you want to talk to a scientist from any other country.
Well, and I'm from Canada, so metric was my thing too.
By the way, it took me a long time to transfer from 9.8 to I still don't know the number.
For what?
9.8 for the gravitational constant. The gravitational acceleration, 9.8 meters per second squared.
Oh, yeah. I don't know it in anything but that. We'll accept 9,800 centimeters per 80 centimeters per second squared. I could do that one.
Okay.
But yeah, I don't know it in any other units. Where was I? Oh, 3,000 Kelvin.
Mm-hmm.
But over time, I was talking about the Doppler effect. So things that are moving away from you, carried away by the expansion, seem to be moving away from you. Their light is redshifted. Well, all that material was moving away from us, and the universe has expanded so much that the wavelength of that light is now associated with a temperature of 3 Kelvin. So we see it as the cosmic microwave background, because the wavelength it is now matches microwaves. So that's the baby picture when they take an all-sky measurement of the cosmic microwave background. And then where it's a little hotter and a little cooler, different places are a little hotter and a little cooler, and that's the hotter spots were a little bit more dense and the cooler spots were a little less dense. Well, the spots that were slightly more dense had stronger gravity, so they started to collapse and fall together and form things like galaxies and stars eventually. And so by looking at that baby picture and analyzing those little temperature differences, you can figure out, well, how much basically the distribution of those fluctuations on the sky has a lot of different parameters that go into it, one of which is how much normal matter is there and how much dark matter is there and how much dark energy.
Okay. Is it fair for me? So is the whole canvas, if it's totally blank, you will only receive the cosmological microwaves. But now, if the whole thing is empty...
if there was nothing else in the universe, then that's all you'd get, yes.
And then by the fluctuation of that, you can see on which direction
and
that
those
has
fluctuations are a few millionths of a Kelvin. So they're or a few hundred thousandths, I guess, like 30 millionths of a Kelvin. So really, really tiny temperature fluctuations.
Wow. It's amazing we can do that, actually.
It is amazing.
When did this kind of analysis start? Like, we have equipment which can measure such a
So the
subtle
spectrum
difference.
was really, the cosmic microwave background spectrum was nailed down as very, very precisely 2.725 Kelvin, I think it is, plus or minus like 0.01 Kelvin. But in about 1990, with the COBE satellite, the Cosmic Background Explorer. And since then, there have been a couple that did, and it also mapped these fluctuations for the first time, but it didn't have really good angular detail. And since then, we've had the Wilkinson Microwave Anisotropy Probe, WMAP, which could see more detail. And then we've had the Planck satellite that was also able to see even more detail. So we have much more precise measurements. One of the hardest parts about it is taking out the galaxy's foreground contamination.
Interesting.
Because you got to worry, like, we live in that galaxy. It's messing it up.
Interesting. So,
but that, of course, all that data is someone else's prized data about the galaxy. So somebody's really interested in studying the galaxy. They want to isolate the galaxy. These other people get all the press, but that data is also used for the galaxy.
So basically, there are like multiple people working in multiple interests on the same data set.
Oh,
collected,
yeah.
Right? Okay.
Yeah.
That's really interesting.
Kind of cool.
Yeah. So when we say we see the universe, basically what we see are all those data, and then we try to imagine by.
Yeah, I mean, you're seeing
You
all
don't
kinds of
actually
stuff. I mean,
see-
you also, I mean, you look at individual galaxies, you look at gravitational lensing of things, you look at, exploding stars, which we think are a particular kind of them, which we think are standard candles. So if they're always the same kind of light bulb, you can figure out how far away they are just by how dim they look. Because, if you put a light bulb further away, it looks dimmer. As long as you're sure it's the same light bulb, you can use that to find the distance. And there's one of the, as long as you're sure it's the same light bulb, it's a tricky. But that's one of the ways they figured out the acceleration, because it's by comparing the distance that you get from the expansion of the universe by looking at the speed. There's a relationship between expansion speed and distance. And there's a relationship between the microwave background or not the microwave background, these standard candles, these light bulbs and distance. And if those don't match, then your model of the universe, how the universe is expanding, is wrong.
I see.
You're basically comparing how those two things fit together. And that's the other thing that drove us to dark energy. There's two things. Well, there's more than two, but the main two are these type 1A supernovae, which are, we think they're all the same kind of light bulb. They're all the same kind of bomb, and you can recognize them through their characteristics. And so we use those, and that suggests that there's dark energy. And the microwave background fluctuations, the models, I mean, lots of parameters go into those models, but one of the ones that you seem to need to make it work is dark energy. And so it's kind of from two different approaches, you're getting a similar, if not identical, result. You're basically saying, oh, there's got to be dark energy. There's got to be dark matter.
Right? The two analyses actually end up converging together.
Yeah,
so
and it's the same with the dark matter. All that stuff about how gravity works between galaxies and inside galaxies gives you about the same answer as the cosmic microwave background.
I heard the assumption a lot, like as long as
it's not like we can, we're not like chemists. We don't get to pick our chemicals and measure them, right?
Mm-hmm.
We can't.
We only have one universe.
Yeah, we have one universe. That's a problem, a statistics problem that I am not qualified to address. But people worry about it. We have one incarnation of random fluctuations to look at. But it's also like we can't just say, oh, let me, throw what I think the light bulb is out there and see if it looks the same. I can't all I can do is like computer simulations and do every check I can think of to ensure that they're same and look for discrepancies in the data. And when people find discrepancies, they go, okay, can I model this somehow? What does it tell us about? Is the object really not standard? And I mean, people are incredibly careful, but I always take, when people say, oh, this measurement and this measurement disagree, I'm always a little bit like, do you really understand your systematic uncertainties? Like, I'm nervous that about grand claims based on discrepancies because I know how much goes in.
Yeah, it's hard to see because so many things actually build on each other.
Yeah.
Anything failed along the way.
And yet, they're very compelling cases, but, people are starting to go, oh, the difference between, 67 and 73 and this number is important. And I'm like, I'm old. I remember when we didn't know if that number was between 50 and 60 or 80 and 100. Like, now you're telling me 67 to 73 is a big difference. I'm not sure I buy it. I agree, your error bars don't overlap, but are you sure? So I'm a bit of a skeptic that way, but...
Do you think eventually we can...
The skeptics aren't always right.
Do you think eventually we can find that without actually, creating new universe or traveling between universe?
I have no idea. That becomes philosophy. I would say, one of the reasons people want to make grand claims about minor discrepancies in numbers is we don't know what dark matter is and we don't know what dark energy is and we'd like some clues. Until you find clues, you really, it's hard to progress on what they are. So the better you can measure anything about the universe, the more you're going to be able to find clues that might help you. I mean, people are looking for clues because, I mean, there are ideas for dark matter, but no one's ever been able to gain evidence that's compelling for any of them.
It's not like we can go there and just grab them and look.
Well, I mean, people are trying. They should be everywhere, just not very many. And the problem is, so if they're particles, then they should be everywhere, but not very many of them. And they don't interact very well with matter by definition, because if they did, we'd see their effects, you know, in terms of other than gravity. They don't have any other, they don't have much other impact. But every once in a while, one should interact with matter. So people are building detectors to try to find them. No one's found any. They might be, I mean, there's all kinds of ideas. They might be primordial black holes that formed early in the universe, and black holes by definition are dark. But black holes are massive and cause gravitational effects that we should be able to see in how they, so gravity is actually bending space, and so will bend light. And so it should act like a lens. If a little mass goes between you and a star, it should act like a lens, and it should actually act like a little magnifying glass. And so you should be able to see stars far away get brighter and dimmer as these wander around. We don't see enough of those. It's hard to measure every option. But anything we've been able to try to measure hasn't panned out yet.
Interesting, yeah. Wow.
So, but, you know, there's lots of other ideas. But dark energy, I haven't seen anybody come up with anything convincing for what it is at all.
It probably is going to take a long time and a little bit of luck, right? So many ideas all make sense,
yeah,
but
and I mean,
implementing each one
the
is so
other
hard.
way out is to say we don't understand gravity on big scales.
That's where the MOND...
MOND is one thing, yeah, modified Newtonian dynamics, saying that on a galaxy-sized scale or at really low accelerations due to gravity, we don't understand gravity. The problem is every time we test general relativity, we get the answer that GR predicts, and we limit the other options, and you're like, I mean, it's not like we've tested every possible regime, but...
Gravitational waves.
Yeah,
right?
but we've tested gravitational waves. Everything it predicts that we can test comes to pass, and alternatives are getting ruled out as we do it. So... people are looking for clues. It's all about, like, how does it work?
I can imagine this is
you can see why I wanted to be a theoretical cosmologist. It just didn't end up that way.
It's such an exciting and frustrating research field.
Yeah.
At the same time, just like I feel like you can spend a whole life learning nothing.
All of astronomy is like that.
Yeah.
I think but you could discover something really exciting. Like,
but any small little tiny discovery is going to be huge.
Yeah, well, I mean, but often it's very incremental. You know, you're just like, oh, you know, I observed this one pulsar and it does this, and how does that fit in, or how does that not fit in? You know, it's just you're always contributing tiny pieces to the puzzle. I mean, most people are contributing tiny pieces to the puzzle, and if you're very lucky, you get a big piece of the puzzle.
Okay. Well, we got kind of drifted.
Yeah, that's okay.
For dark matter, but now let's go back to interstellar media. And
yes.
You correct me on the typo, which basically means the letters doesn't quite make sense for me. So I'm just gonna spell them out.
Yep.
What are SETHI or SETHI?
Yep, SETHI and GALFA.
Galpha.
FA. Sorry, yeah,
Galpha.
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 Yeah, Galpha.
Okay. And
so
what's the first one? SETHI.
SETH1.
SETH1 and
so
Galpha.
SETHI. So
Yep.
H1 neutral hydrogen.
Yep.
We got to the H1 part. Okay. So the SET is search for extraterrestrial, and it's kind of it's a pun. In Puerto Rico, there's this giant 1,000-foot across radio telescope.
Mm-hmm.
You might have seen it in movies. It's called Arecibo, and it's really good at detecting faint radio waves. So it's one of the, so some people I collaborate with, one of their projects is to try to detect ET, signals from ET. They're looking for radio messages from extraterrestrial civilizations. And So that project was called the Search for Extraterrestrial Intelligence, and their particular project is the SETI at Home project. You can actually take their data from Arecibo and run it on your computer when it's doing nothing and contribute to analyzing these data, looking for alien signals. It's hard to get telescope time to do this search. So they basically created an instrument that would just look wherever the telescope happened to be pointing and collect data at 21 centimeters, and just hooked it into the system. And so wherever the telescope's pointing, they're observing, looking for data for wavelengths near 21 centimeters, because that's one of the wavelengths that goes through the universe well. So we'd expect it'd be one you could use if you were trying to signal someone. And after a while, they realized, hey, this could be used to map neutral hydrogen, which also emits at 21 centimeters. And so basically, it's just the telescope's pointing all kinds of different places in the sky, but over, 5 years, it builds up information about every spot on the sky. So for every spot on the sky, at least the part that goes above Puerto Rico, every part on the sky that's nearly overhead at Puerto Rico, you get information about how strong the 21 centimeter emission is, or from neutral hydrogen, at every speed towards or away from you, every velocity. So you have a little data cube. And that's the search for extraterrestrial neutral hydrogen, because now you've used it from the SETI data, and now you have the SETI data.
So how do you discover there is a H1 there, H1 shell there?
So
by looking at the data.
Yeah, so basically you look at the cube. So the way I'm doing it, there's multiple ways to do it. You can look for expanding things. The thing is, as these things, I said they expand. As they age, they're going to slow down and cool. And as they slow down, you're less likely to see them by looking for signs of expansion. So I'm just going through the maps at each velocity, looking for things that look circular or oval or enclosed, or at least some sort of hole with walls. And having students search, and we measure their properties, and we do whatever we can to analyze them. And I want to say 2014-ish, I published a paper that was based on the SET-H1 data.
I see.
Since then, they got there was at some point an upgrade to Arecibo, and they were able to get better data with a higher resolution on the sky. They could see more detail, and with some better calibration. They actually designed the data taking to do a better job of measuring the brightness of the neutral hydrogen in every location. And that's the GALFA data, Galactic L-band Feed Array Neutral Hydrogen Survey.
So basically what you're referring for those two names are two data sets.
Yeah, they're two data
at
sets.
Different resolution from different time.
And right now we're going through the GALFA data set, and what we're finding is that shells that look like perfect round bubbles in the SET-H1, the SETI at Home spin-off data, look incredibly complicated and messy in the GALFA data. The more detail you have, the more you're seeing the complexity of interactions, because multiple stars have exploded in the region over time, and all those bubbles are interacting, and it's messy and it's hard. So we've been focusing most on the parts of the sky where the GALFA data are the best available. There are parts of the sky where there are other surveys that do a good job, and there are parts of the sky where they don't. And we're focusing on the parts where other data sets aren't as good, and also there's less hydrogen gas, so they're simpler. Because we're trying to learn how to handle the complexity of the data.
So when you say handle the complexity, I was thinking about decoupling, decompose those interactions, and eventually get a picture of every single shell, or is that the
I think
purpose?
It's not. Well, one of the problems is you can't completely relate distance to speed. Because stars, when they explode, might have some random motions relative to the average.
Yeah,
and
it's not
so,
homogeneous as a topic. Yeah.
No, it's it's messy. Yeah.
Okay.
That's. I think that's above what I'm gonna try to tackle.
Yeah, for now, just the clean ones. Right?
Well, and just right now, I've actually got a project of having a bunch of students go through the list from that previous paper and look at them in the new data and go, what would I say this is in the new data? Like, not look for anything new, just if I just look at the things we found before that hadn't been previously found, that paper was on things that hadn't already been found, would I still call it what we called it before? Or would I say it's a completely different thing now? Would I call it 4 things? Would I call it 5 things? Would I say, no, I think that's just a random superposition of things that happened to look real? Like, because when you change the detail of the data, it really does. And so it's like, I think that's important. We have all these catalogs from different data sets, but nobody's, as far as I can tell, has really gone, okay, things look so different with the different data sets that you can be fooled into thinking you're looking at one thing and not another. And I'd seen that some comparing my stuff to previous, but I'm seeing it even more now that I'm looking at, like, I'm very familiar with both data sets, and I'm like, ooh.
What's the time gap between both data sets?
Not that long.
So it should be a small compared to the time scale.
Nothing in the sky
H1
should be
shell.
changed. Nothing that we're looking at in the sky should be changing on those time scales.
Is it fair for me to say, like, because you point to the telescopes to the sky, the data you received is basically projected into a lower dimension? That's why you see a lot of overlapping happening together?
Yeah, I mean, you try to get the third dimension back with the Doppler effect, but
distance,
it's not.
okay.
It's related to distance usually because there's sort of a pattern of motion in our galaxy, but there's also random motions, so it's not a perfect.
I see how difficult that is.
It's not pretty, yeah.
Okay, wow. So that's one project you're doing.
Yep.
And you also mentioned in your slides another one, which is finding exoplanets using, I would say, the similar method with Doppler effect.
No, pretty unrelated.
Yeah.
So,
what is exoplanet and how do you find it?
So I got into this project because I was at a conference where I was talking to my colleague who I work with on this neutral hydrogen stuff. And he said, I wish I could get a student to help me with this project over here. And I'm like, well, what is it? And he told me, I'm like, I'll do it. It sounds fun. So then I had to learn.
That's the reason when no student ever get any fun project. Right? It's blocked right at this level.
But he couldn't find a student who wanted to work with him. So I was like, heck, I'll do it. It'll take me a while because I got a heavy teaching load, and you're not at a place with a heavy teaching load. He's on soft money, so he has his own challenges, but teaching is not one of them. And I'm like, and so it grew out of that. And then I had to go learn everything because I knew nothing that was.
Walk us through the process. How did you learn from scratch how to do this?
Well, so let me tell you about the idea, the concept, and then it'll make more sense. So astronomers, an exoplanet's just a planet around another star. And, I got to subtract. 30 years ago, we didn't know of any, really. Yeah.
1990, 1980, yeah.
Yeah, we didn't know of any in 1990. I know this. We knew of none in 1990. And now we know of thousands. And one of the ways, there's multiple ways we've found them, but one of the ways is if you picture a planet going in an orbit and its orbit is such that it passes between you and the star, it's going to block a little starlight and make it get dimmer. Mm-hmm. And that's called a transit. And that's how most of them are being found. You have to be lucky because if its orbit's not right edge on, it's going to go above or below. But a lot of them are discovered that way. And the project, my colleague had been inspired by some light curves there, where you all you're really seeing is the dimming. All you measure is how the star is dimming, and from that you try to figure out everything about the planet and its orbit that you can. And somebody had showed him some light curves that really didn't look normally. He's like, I think someone's winking some mirrors at me. Just kind of thinking off the cuff. And he said, well, wait. A lot of these planets are close enough to their star that they're tidally locked. They have a dark side. So, like for our moon, one side always faces us.
It never rotates, right?
Right.
That's what
well, it
mean, right?
rotates,
Yeah.
but it rotates once per orbit, so it's always facing us.
Yeah.
Well, around some of these stars, you could have planets who always has one side facing the star. Okay, so one side's facing the star. Those stars turn out to be very cool and dim So stars that have, around some of those stars, you could have one side facing the star, but still have the planet in what we call the habitable zone, the region where liquid water might be able to exist on the surface. If this planet's too close, it's too hot. If it's too far away, everything's frozen. So if you're worried about looking for signs of life elsewhere, you want to focus on things in the habitable zone. Just because, although, can of worms, what does life need? Does it need water?
Liquid water.
Sample of one. Earth. So, but you look for what you know. So you're looking for liquid water. He's like, well, if there's a perpetual dark side, maybe they want to light it up somehow. So let's send out light mirrors. Light being going to sound heavy. Couple thousand pounds, would weigh a couple thousand pounds here. So 1,000 kilograms. But a kilometer on a side, 1,000 meters on a side. So over 10 football fields on a side. Mirror, and redirect light onto the dark side of the planet. How would that affect the transit light curve? So if you put up a whole bunch of these to get enough light onto your dark side to do something to make it useful, or maybe you want to terraform a planet, make it warmer, or something. How would the fact that you've got all these things out in orbit affect how the light gets blocked as the thing goes in front of its star?
Lighter, like smaller.
Well, it's going to block more light, but it's not you've got a cloud of these. You're not going to have it's not just going to make the planet look bigger, because you're going to have sort of a region where some light gets between the satellites to you and some doesn't. So if you kind of imagine it, you have like a semi-transparent ring around your planet if you're looking at it in cross-section.
Okay.
And so we modeled how that would affect the light curve of the transit. And if you found something that was like that, you'd have to worry about, is it a ring around a planet? Like Saturn has rings. But we have thought of ways to distinguish those things. And we analyzed whether they'd be detectable in the data that existed.
So I'm a little lost here.
So, yep.
Basically, if you don't mind,
This is one of those things where a picture makes life so much easier, but we don't have that.
If there is a mirror and you actually you should reflect all the light of the star, some of the light of the star to the dark side of the planet, exoplanet.
Yeah, you're lighting up the exoplanet.
Then you are basically going to detect it almost similar as a ring.
Yeah, so it's not just one mirror. We're sending up millions of them.
Okay.
So we're sending up a whole cloud of these things.
But are you just saying hypothetically, or actually we did send so many mirrors?
Yeah.
We did send so many mirrors?
Well, no.
Oh, okay.
But suppose that an extraterrestrial civilization
the analogy is the mirrors are the ring.
Yeah.
Oh, I see now. Okay.
So basically, if some civilization wanted to light up the dark side of their planet, they'd send up a whole bunch of these things, because it's easier to send up a whole bunch than to build something, half the size of the planet. Yeah. To one big mirror is hard. Small ones are easier. Okay. And then once you've got a whole bunch of them flying around your planet, you're going to have this cloud of things around your planet that blocks some of the starlight, but not all, when the whole structure passes between you. That's going to have an impact on the light curve.
And that's the light curve we observed.
Yeah.
And we are trying to guess, okay, that's probably what's happening.
Oh, you were thinking about what they're seeing. No.
Okay.
We want to, now there's some climate issues. They're heating up their planet, which is why I said maybe they want to take a planet that's uninhabitable and make it habitable. I mean, there's reasons you could want to do that.
Can I do the same thing with Mars?
People have talked about terraforming Mars. This would probably be one way to do it.
Okay. Other than just go there and nuke the North Pole, this sounds way better.
There are some technology issues. We don't quite have it yet. But my colleague tried to sort of extrapolate beyond what we can do now, but not so far as to be unimaginably difficult.
I see.
And we basically figured out, what would happen to the light curves, and could we detect it with the current data? The answer was not yet. Our data aren't good enough to tease this out easily.
You mean don't have enough data, or the data doesn't have enough resolution?
It's not sensitive enough. The differences excuse me. The differences look big enough until you realize that you're not actually looking at the planet or the planet plus the thing. You're looking at the planet plus this cloud of mirrors against the best fit model all the other possible parameters could fit that would hide it. So any model of your light curve has a lot of things that go into it.
Mm-hmm.
Some of which can mimic, not completely mimic this, but can make the effects, suppress the obviousness of the effects by taking pieces of them. and you get the answer for the other parameters wrong if you don't think this is there, but it hides the effects. It's just the noisiness of the data. These things are far away. They're, it's how much data can you collect, and the star is dim.
So you're trying to reduce uncertainties by observing more data, but now the data itself actually contains additional noise.
Yeah, data is always noisy.
Yeah.
It's like you're just not getting enough signal. Stuff is faint. So, and you're trying to divvy it up with time. One way to look at faint things is to open your camera shutter for a long time and collect a lot of light. But if you're trying to look at differences as time goes by, you can't do that. You just need bigger telescope. And even the James Webb Space Telescope, when we first did this project, we thought it might be able to do it for at least some of the situations. But we were basing it on the estimates of its sensitivity in a certain filter band. And since then, we have actual measurements from that was estimates based on design. And now we have more accurate estimates, measurements of the thing that's built but not yet up. It's like, it's not as good. So that combined with sort of a couple other things, just it's going to be really hard for the foreseeable future to see these.
Interesting.
Mm-hmm.
Yeah.
We also looked at if you just did a belt of satellites, just put up because right now we have a geosynchronous belt of satellites,
mm-hmm.
right? Because for TV satellites and cell phone satellites, they don't want to move. They want to always be above the same spot. We want that. We said, what if they have a really dense belt? And that wasn't our idea. That was someone else's idea. But he thought it would be fairly observable. And we went, we don't think so. We think you've left out some of these suppressing effects of, well, when you just fit a model without what knowing what's going on, what could you get just not including this in the model? And how obvious is it then? And it's not as obvious as he thought. If you include some of those more realistic effects. But I had to go learn about transits. I knew nothing about transit light curves. Getting back to your question, what do you do when you take on a new project? Knew nothing about transit light curves. I didn't know how you modeled a transit. I went around at this conference. I started going to the posters on transits. Started going to the talks on transits. Turns out I had to learn about limb darkening of stars, which is the sun. All stars are a little bit fainter at the edges than the center. And that's not that hard to understand, but you have to be able to model it well to do this modeling of the light curve. And so I had to go learn a whole bunch of stuff that I didn't know much about. I had to go, well, which stars would have habitable zones with synchronous, with these perpetual night worlds in the habitable zone? Oh, so I got to go find somebody who tells me which planets where will be in that state, and then compare it to a habitable zone and see what. So it's just I had to go learn about a lot of different things.
One thing leads to another until you start to have a piece of information putting together to see the
so
structure.
It took a while, but it was kind of fun. I mean, it was fun, and now now I've got. My colleague always envisioned part 2 of this project would be analyzing the effects. So now you've got big, lightweight mirrors. Light exerts a force. If you've got a big enough, light pressure. If you've got a big enough area and not much mass, the light from your star is going to affect the orbit of your mirrors. So now we're trying to model that and figure out which orbits will be easier to keep where you want them fuel-wise. Because it's going to take fuel if light's pushing off course constantly. But it's like, well, wait, we don't actually want to light up the day side of the planet, only the night side. So it's constantly getting pushed when it's in one place, but it's interesting, and we're running simulations on that now to see what happens. And sometimes radiation pressure is really important. Sometimes it does something odd where it elongates the orbit and then the orbit starts to precess. and it actually never hits the planet or escapes. It just does this kind of little dance. So even though there's a lot of light pressure and it's important, and it's affecting where the mirror is at any one time, it isn't totally destabilizing it.
I ran some simulations from computational physics experiences before. Just listening to you describing the problem is giving me a headache.
Oh, it's given me a headache for years now.
It's just like, okay, how I was supposed to one thing and after another, and everything came into play.
In this case, you go and you find the simulator package called Rebound, which models gravitational interactions and is designed and has the integrators and everything all in it. So I don't have to worry about designing an integrator. And what I have to throw in is the additional forces and so the radiation pressure and just how to get it to and figure out how to get it to run the situations I want and give me the output I want to analyze, which is in itself enough of a challenge.
Is the radiation pressure strong enough to be factored in the model?
It's absolutely important. The first thing I did is I had a student calculate the acceleration due to radiation pressure and compare it to like the acceleration of the planet's gravity and the star's gravity. And in some of the situations, it's really important.
I see.
In others, it's less so, but it's always at some level. It wasn't tiny. I wanted it
first order.
Well, I mean, it wasn't so tiny we could go, oh yeah, we don't need to include it. So.
I see. So eventually, once the simulation, assuming ever we will be
many simulations.
Once we can do the simulation and we verify certain kind of hypothesis, is it fair to say like there's a very high chance there are civilizations?
I don't think we know enough about what civilizations are out there. I think there's probably life out there, but we don't really know how life got started, so we don't really know. And we already touched on what does life need. Would it look like Earth life? Earth life's already pretty weird. It, can hibernate. There's these weird things called tardigrades. Have you ever heard of tardigrades? No. Oh, they're also called like water bears.
Oh, that I know, yeah. They can survive in vacuum, right?
Yeah, they can survive in a vacuum for a while. They can experience high radiation. You freeze them. Basically, they just hunker down and like hibernate almost, and they can come back to life. And you're like, really? Really? And that's an Earth thing. But they do need water eventually, or they will.
But I mean, they will still survive. They need water to come back to life.
Yeah.
Right?
Yeah.
So it's almost like an ideal creature you want to put on a spaceship. If they're intelligent.
Yeah, if they're, which they aren't. They're also tiny, microscopic little things. Look up sometime the pictures. If you've never seen the pictures of them, they look so freaky.
I've seen like they have like 6 legs. There's like a small
they got
plate.
Suction mouths.
Yeah.
And they look really,
yeah.
There are these really strange things. So I think there's life. There's probably, if there's life, I would guess there's intelligent life somewhere. Space is really big. Universe is really big. Whether it's close enough to think about having a conversation even over decades, I don't know. I don't know how likely it is there's even another one in our galaxy. I got no idea. I mean, I think the whales are probably intelligent, but they're not sending out radio signals.
Do you think that radio signal will be the ultimate way to communicate with
we're looking at radio signals. We're looking for variability in visible light more and more. The time domain in visible light's opening up, although that opens up a can of worms. The Starlink constellation, that's goal is to put global internet. Those things reflect sunlight and are making a mess of visible.
And those are stronger than the radiations?
Well, the visible light, the problem is those things are going to be visible to telescopes all the time if they get the 30,000 or whatever they want. So right now, as we're getting to the ability to look for short-term signals on large parts of the sky in visible light, it might get hard for us to avoid the satellites. But if you think about radio waves are one good way to send signals, but we're sending fewer and fewer of them. More and more of our communications is run on fiber optics and less and less across the air. So more and more of our communications is done like through fiber optics across Earth.
Fiber optics. Okay,
yeah, fiber optics. and less is like just sent out with
Wireless.
transmitters. Yeah. And so, like, if you're expecting to detect someone's stray stuff, and in fact, we can't really detect stray stuff except for the nearest places. It'd be too faint. It'd have to be an intentional signal. It's worth checking. It's worth looking.
People have been monitoring that thing for more than how many years?
Yeah.
I remember the
it's-
one in Puerto Rico is doing that. Yeah.
Yeah, I mean, they've been looking since the 60s or 70s.
60s, okay.
But, I mean, it's one of those, well, you don't expect to find anything on any given day. But if you did, it would be really exciting because, is there someone out there is a cool question.
Are you excited about going to Mars?
I get motion sick, so I'm not going. The other thing is, I think sending people is hard. I know how much astronauts who spend a long time on the space station, it's not good. No, not having gravity is bad for your body. So if you're spending, say, 3 months getting there, your body's not going to be in great shape when you get there. Not to mention the radiation.
Cosmology ray? Cosmology ray? Ray?
Cosmic ray.
Cosmic ray,
Yeah, cosmic rays. High energy particles from the sun and from elsewhere. Even the space station's close enough to the Earth to be protected by the Earth's magnetic field. And so when you get further out, and when we sent people to the moon, it was 3 days out and 3 days back. It wasn't a long-term exposure. They didn't have time for their muscles and bones to atrophy and their blood circulation to get messed up from lack of gravity. They didn't have time for there to be enough radiation exposure to be terribly hazardous. But going to Mars, all of those are issues. So I think more than any of the other technological issues, I think that's the biological aspect of even traveling to Mars is hard.
Yeah. It's strange to see when people spend too much time in space station, when they come back, they cannot even walk.
Right.
They need
So
to
now
chill
you
out.
want them to land on a planet where there's no resources. There's no infrastructure for them.
Yeah.
I don't know how that's
Several
going
months
to work.
one way, several months the other way coming
Yeah,
back.
I mean, the fuel-efficient orbits, the ones that don't use much fuel, take, I think, 3 months minimum each way, I think. I mean, if you were willing to burn a lot of fuel, but the more fuel you're trying to burn, the more you're carrying, and then
The
the
heavier,
harder it
huh?
is to get off Earth, and it's,
Seems like a paradox.
yeah.
What about moon? I think NASA is actually restarting some programs on.
I think the moon's a better starting place. People are like, oh, we've been there. I'm like, yeah, but we haven't been back in how long? So I think it makes more sense to start there and practice.
I guess that's what they're trying to do, right? They're
Yeah,
trying
I mean,
to
that makes more sense to me than
manufacture
thinking
and
Mars. But
launch on the moon.
yeah, I mean, I think that makes more sense just because it's closer, so you practice a lot of the stuff. But it's not quite the same as Mars. Weaker gravity on the surface and no atmosphere, so the landing is different. And some of this, there's sandstorms on Mars, bad sandstorms. So, what do you do when you're, do you want to be an astronaut in one of those suits in a sandstorm? I don't think so.
Even just watching it in what's the movie Interstellar? That was not a sandstorm. That was a tsunami.
Yeah, there you go.
It's already
Yeah.
very, very scary.
Yeah.
Interesting. So do you believe in? Do you think eventually we will travel outside the galaxy?
I think outside the galaxy, I don't know. I think other stars, if our species survives, yes.
How long do we need to survive before we do that?
I don't know. I think it's got to be thousands of years. I don't think it depends. If you, unless the laws of physics are nothing we know about, unless the speed of light is not a limit, and basically our technology right now would take sort of 40 or 50,000 years to get to the nearest stars. So I'm not real hopeful that right now we're headed there. But even if you could get going a lot faster, which takes enormous energy, and I feel like there'd be better places to put that energy, You're still talking years, and so you're still talking significant, life support issues, or you're talking generationships. Like, let's say we got it down to 200 years. We either need suspended animation or we need people willing to, like, go have kids on the ship,
Yeah. After 6 generations, they don't want to be on the mission anymore.
I asked this question in intro astronomy class, and I usually get 2 or 3 people willing to go, and I'm thinking, are you nuts? But,
We will wait until they pass the test. Maybe they will stop saying, like, I don't want to go anymore. Once I know I'm really going, then no. I could never understand that. I just, like, go to the Mars, even just go to Mars, or just, even just habitate on Moon for 2 years or something like that without communication or without coming back. It's crazy.
It does not appeal to me, but I think it's exciting to think about. But the more I know about how hard it is, but then I guess I'm just a pessimist. I look at stuff and go, that's hard. And I look at some of the measurements people are making now, and I'm like, 20 years ago I'd have said they were impossible, but somebody's doing them. So
who knows? So if we already have talked a lot. So if I want to close with this question, so to see the future of human species, right? People talk about interstellar traveling or going to Mars or going to Moon and probably just reverse engineer climate change and everything. I have a sense, like, do you want to bet your money on just we still stay on Earth? And probably that's the...
I don't know that I have a bet. I'm like, the future will be what the future will be, and there are so many things. There's a small chance we get, wiped out by a large asteroid in the next few hundred years.
We have one coming today, right? 5 o'clock.
I didn't know about that one. The more we look at, we're getting better at knowing which ones are out there, but there's still, I don't think we're at the point of species killing. We think we've found all those and there's nothing imminent, but there are things that could do significant damage. Like, I think a couple 100 meters across, couple football fields across. If a rock like that hits real fast, it's not good. And it would be very disruptive to our progress because you just have, a whole region's devastated. And I just think our resources are going to end up going to, moving people away from coastlines and stuff. If climate change results in the sea level projections that most climate scientists, 99% of them or something, say, yeah, that. So I'm just like, I feel like our energies are going to get redirected, is my guess.
Great.
But I don't know. Maybe, but we don't know what dark energy is. We don't know what dark matter is. Maybe there's something completely unexpected gonna happen when we start to figure that out.
Sallmen worked before in history, right? Every time we need something always pop up.
Well, and that'll be true right up until our history ends, right? Yeah. And then nobody will know anymore. You can
never just blindly plan on that.
Whenever that luck runs out is going to be the end of our history, probably.
Yeah, just crap.
Anyway, if we haven't done it in 5 billion years, it won't happen because the sun's going to be a red giant and will be burned to a crisp. So,
yeah, that's not something I want to worry about. So.
But, if you count from 1 to a billion, one number a second, it'll take you 30 plus years. So I'm not too worried about the 5 billion years from now moment.
Sometimes a short life expectancy is kind of like a bless for us, right? So we don't have to witness so many tragedies.
Well, yeah, there's a lot of things that could happen in the next, few thousand years. I'm like, I'm not going to panic, just not going to panic about every possibility, like the asteroid hitting or whatever.
So if I could ask for some of your students, like, how do you think studying astrophysics changed your life?
For me? Mm-hmm. How did it change my life?
Or you were just like this before you studied?
I don't know. I don't know. I just think it's fun to study what's out there for the sake of studying what's out there. Because, often the technology we use in astronomy spins off and has, uses in other fields and applications, but we're not setting out to, cure cancer or anything. I just think it's fun to discover how stuff works. And I think that's what physicists like to discover, how stuff works. And that's what we're trying to do. And I didn't want to just, I wanted to look at the stuff out there. And there's just so much variety out there. But I'm always telling my students at the beginning of the semester, okay, every other course you take in college is about Earth. I have one semester for the rest of the universe. Do you see my problem? We're not going to get to everything.
Okay, great.
So.
Well, thank you so much for joining us.
No
that was
problem.
fun to talk.
Good.
To talk. Yep.